Good morning all. This is Dr. T. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In the today's lecture, we will discuss the programs problem related for 8051 timers and counters. These slides are prepared by referring the textbook, the 8051 microcontroller, authors Kenneth Ayala, publication Cengage Learning. The first problem is generate a square wave of 2 kHz, 50% duty cycle, that is symmetric, on the port 1.5 bit. Timer 0 is used to generate the time delay. Assume the clock frequency is 11.0592 MHz. So the problem here, we have to generate a square wave which is a symmetric signal. So this time period T1, and if it is T2, the total time period is T. Then T1 is equivalent to T2, which is equivalent to T by 2. And the frequency of this one is, the frequency is 2 kHz signal we want to generate, which the signal we are going to be generate on port 1 5th bit, through which we are going to generate a square wave. Here we are going to be pass logic 1 for T1 duration, logic 0 for T2 duration, again logic 1 for T1 duration again. So on port 1.5, we will send 0, 1, 0, 1, 0, 1 or 1, 0, 1, 0, 1, 0. For each and every pattern will be sent for the T1 time. For 8051 programming for timers, first we have to load the T mode register for timer 0 or timer 1, depending upon the mode of operation. Then we have to calculate the load value, that is count value, in THX register as well as TLX register, depending upon either timer 0 or timer 1. X indicate either it is 0 for timer 0 and 1 it is for timer 1. Then start the timer by setting the TRX bit in TCON register for timer 0, TR0, for timer 1, TR1. Then every time we have to check the TFX bit, TF0 for timer 0, TF1 for timer 1, indicating whether overflow is occurred or not. If it is not occurred, we are going to be repeat for reading the TFX pin until it is equivalent to 1. Once the timer overflow is occurred, then we will stop the timer by clearing the TRX bit in TCON register. After that, we have to clear the overflow flag, that is TFX bit. For repetition of the same, then we have to go for step 1 to 7 for the delay again. So in the problem, the given values are, the oscillator frequency is 11.0592 MHz. The clock frequency, it is given as the oscillator frequency divided by 12, which is equivalent to 11.0592 MHz divided by 12, which will give us 921.6 kHz. This is the frequency of clock. Then the time period of T clock is equivalent to 1 by F clock, which is equivalent to 1 by 921.6 kHz, which will give us 1.085 microseconds. For the square wave, we want to generate the signal of frequency 2 kHz. Out of the 2 kilohertz, half of the duration it will be in logic 1 and half of the duration it will be in logic 0. So the time period of the square wave, it is given as t is equivalent to 1 by frequency of the square wave, which is equivalent to 1 by 2 kilohertz, which will give us as 500 microseconds. Out of this 500 microseconds, for 250 microseconds, it will be at logic 1, and for 250 microseconds, it will be at logic 0. The square wave is at high state for 200 microseconds and low state for 200 microseconds. The count, how much count we have to place, it indicates the time required for the signal divided by, for each clock pulse of whichever we have calculated here, divided by that, it will give us how much count we have to load or how many counts we have to take place. So here the count will be calculated as the required time is for 250 microseconds divided by each clock frequency is 1.085 microseconds. So we have to pass total 230 clock pulses for generating a square wave with duty cycle of 50% duty cycle for 250 microseconds. Now here we will take the timer in mode 1, which is a 16-bit timer. The maximum count is 2 power 16, which will give us as 65536. Right. The count to be loaded in the registers is maximum count, that is 65536 minus 230. They are in decimal. Actually, in hexadecimal, the count, maximum count is equivalent to FFFFH. The decimal equivalent we are taking. So the load which we want to load is equivalent to 65,306 in the decimal. In the hexadecimal, it is equivalent to FF1AH. Here, whatever the timer we are using, either timer 0 or timer 1, this we have to load into the respective registers. That is either T0 or T1 register. So now out of these 16 bits, the lower 8 bits, the FF1A is a 16 bit. Out of this 16 bit, the lower 8 bits will be passed to TLX register. The upper bits will be passed to THX register. So the count which we want to load into TL register is 1AH, and the count which we want to load into THX register is FFH. And the square wave which you are going to be generated is on port 1 5th bit. The steps for this one is configure timer 1 in mode 1, that is for 16-bit case. Load the count, that is FF1A, by writing TL1 and TLH1 register. The TH1 is loaded with FF. The TL1 is loaded with 1AH. Then we have to start timer 1 by configuring or by setting the TR1 bit in TCON register. Check timer 1 overflow by checking TF1 in the TCON register. If TF1 is equivalent to 1, it indicates that required duration, that is 250 microseconds, is done. Then you can go for complementing the value. Once the overflow is occurred, then stop the timer by configuring the TR1 bit as 0. As the square wave is done for logic 1, then we have to go for logic 0, again logic 1. So we go for complementing the port 1.5 bit for each iteration for generating the square wave. Then clear the overflow, that is TF1 will be cleared here. Then reload the time with the same count, because we are not configured the timers in auto reload mode. So after this step, again we go for loading the count into the T1 register. For configuring the T mode register. As we are using only timer 1, timer 0 bits we will write as 000. For timer 1, we are configuring in timer 1 in mode 1 by configuring M1, M0 bits as 01. Next, C by T bar for timer 1. As we are using for timer, configure this bit is equivalent to 0. The enabling signal is not required. That is gate signal we will write as 0 because internally we are writing programming for timer. The value which we have to write for T mode register is 0, 0, 0, 1, 0, 0, 0, 0. This is the value which we want to write into T mode register. In the hexadecimal, it equivalent is 0 and this equivalent is 1. So 10H we have to write into T mode register. So for that we will write the instruction as move T mode comma hash 10H. As it is immediate data, hash is required in 8051 programming. So now the T mode is configured for timer 1 in mode 1. Then we have to load the count which is FF1A. 1A will be loaded into TL1 register, FF will be loaded into TH1 register. Move TL1 comma hash 1AH. Move TH1 comma hash FFH. Whenever the count, if it is starting with the alphabet, it has to be prefixed with 0. A, B, C, D, E, F. In the hexadecimal representation, if it is starting with the count, prefix this one with 0. Whereas here it is starting with 1, no need to prefix with 0. After loading the respective registers, then we will program the start bit for timer 1, which is TR1. Set B TR1. This signal will make the TR1 bit will be 1, indicating the start of the timer run for timer 1. Once the timer is on, for every clock pulse, the count will be incremented from FF1A to FFFF. Once it is reaches to FFFF, the next iteration it will be go for 000H. Whenever this overflow is occur, it is going to generate the overflow. As it is timer 1, we can see this one on TF1. Now we want to check the TF1. If TF1 is equivalent to 1, it indicates the timer activity is done. If TF1 is equivalent to 0, it indicates the overflow is not occur. So go for reading again TF bit. So for that we will write J and P. That means jump if no bit on TF1, where we have to jump to the same instruction. Read the TF1 until that bit is equivalent to 1. So if the bit is equivalent to 0, if the TF1 bit is equivalent to 0, go to label 1. Go to label 1. Else, that is, if the TF1 bit is equivalent to 1, then go to the next instruction, indicating the time period which were allotted for the delay, it has been done. So then we can go for further actions. So this will be iterated continuously until the overflow is occur. Once the overflow is occur, this condition is fails, so it will come out of the loop. The next instruction is we have to stop the timer by clearing the TR bit. So by writing the TR bit is equivalent to 0, then the timer 1 will be stopped. Once the timer 1 is stopped, then we have to complement the bit of port 1 5, because every time we want to generate a square wave, that means by passing 1s and 0 continuously. So first initially if it is 1, then go for complementing it, then I'll get the complemented value. Right. CPL P 1.5. Overflow is already checked. So clear that overflow flag. That is CLR TF1. So by this TF1 will be cleared. For getting this pulse, again we go for loading the count. So S jump to label 2. This label 2 will be placed for placing the count again, because the count is changed from FF1A to 0000. That 250 microseconds is done. For the next microseconds, 250 microseconds, then we have to load the count into the respective registers. So the jump will be takes place for loading the TL1 registers. So the program at a glance we can see. Move tmode, hash 10h. Move TL1, 1AH. Move TH1, hash 0FFH. Start the timer by writing the instruction set B TR1. Check for TF1. If TF1 is equivalent to 0, go for iterating here only. When TF1 bit is 1, come out of the loop. Here we can go for clearing the timer run 1 bit, that is for stopping the timer. Complement the port bit P1.5, clear, overflow, then S jump L2. So now here we are complementing the P1.5 every time. We are not initialized. So earlier it may be 0 or 1. So next every time it is going to be complemented 1. So suppose if I want to make the signal has to be start with logic 1. So here we will write the instruction. One more instruction we will add at the top, which is equivalent to set B port 1.5. So it is going to be generate first logic 1 for 250 microseconds. Then it will be go to logic 0 for next 250 microseconds, because of which we are going to get a square wave of frequency 2 kilohertz. If the signal was to generate like this, initially 0, then 1, here we can clear the port 1.5 bit. So this is the program for a generation of a square wave using port P1.5. Timer 1 is configured in mode 1. The next one we will see, the next program. The following program is used for creating a square wave of 50% duty cycle with equal portions high and low on P1.5 bit. Timer 0 is used to generate the delay. Analyze the program. So here they are given the program, then we have to find what is the frequency which they are taken for a generation of a square wave. So this program will generate a square wave with 50% duty cycle. That means T1 is equivalent to T2 is equivalent to half of the time period of the square wave. Right. This we are generating on port 1.5, which is used for generating the wave, and timer 0 is used for the delay purpose. Now we are going to analyze the program. By that we can see what is the frequency of the square wave which it is generated. Next, move T mode 01H. So the T mode register is written with 01H, that means 0000001. This indicates mode 1 for timer 0, and this is for timer 1. Timer 1 we are not using. Next, the timer 0 is configured as timer. This is gate bit is not required. Move T mode, 01H. This indicates the timer 0 is configured in mode 1, that is 16-bit timer. Next, move TL0, 0F2H, TH0, FFH. So here the count which it is going to be stored in T0 register is FF2. This it is loaded into TL0, this it is loaded into TH0. For every clock pulse, this will be incremented by 1. Until what portion it is going to be incremented is Once it reaches to the maximum count FFFF, the next clock pulse it is going to generate 000. Whenever this overflow is occur, this it is going to generate the overflow on TF0. Next, complement P1.5, call delay. This is a call function. A indicates absolute call. Delay function will be called. So here in this delay function, it will wrote for set B TR0. This is to start the timer 0. Then check for JNB TF0 L1. It is for checking whether overflow is occurred for timer 0 on TF0 or not. If it is not overflowed, stay in the same loop L2. Whenever overflow is occur, come out of this, stop the timer, clear the overflow. Then RET, it is for return from the subroutine to main program. So this is the main program and this one is subroutine. After delay function, sjump to L1. So again loading the count, right? So now this program will generate a square wave. Now we want to find out what is the frequency of operation. So the first instruction is move T mode, 01H, which indicates the timer 0 is used in timer mode 1 and it is used as timer rather than counter. The next instruction is we have loaded the count into TL register and TH register as F2, FF, H respectively. So as we are using the two registers and mode of operation is mode 1. So it is 16-bit timer and the count is FF, F2H. The maximum count which you can have for 16-bit is FF, FFH, right? Complement P1.5, it is for toggling the square wave for logic 1 and logic 0. A call delay, this is for call to a subroutine. Sjump L1, after the square wave is generated for logic 1, go for iterating by loading the count till the operation, that is a overflow clearing iteratively until how many clock pulses which we require. In the delay program, we are having time run. TR0 is set, so timer 0 will be start functioning. JNB TF0, L2. So when overflow is not occurred on TF0, iterate in the same instruction until this bit is equivalent to 1. That means the overflow timer 0 will be rolls to 000H from FF0H. So whenever this overflow is occurred, then the TF bit will be set to 1. Once the overflow is occurred, clear the TR0 bit to stop the timer 0. CLR TF0 bit, it is for to stop or to clear the overflow which is occurred on timer 0. RET, which is returned from the subroutine. So now here we are loaded the T0 register with the count FF, F2H. For calculation of the frequency of square wave, the assumed XTAL1 for 8051 is 11.0592 MHz, which is the oscillator frequency. From this, we will calculate the clock frequency. F clock is equivalent to 11.0592 MHz divided by 12, which it is going to generate 921.6 kHz. The clock period time T clock is equivalent to 1 by F clock, which is equivalent to 1 by 921.6 kHz, which will give us 1.085 microseconds. So these clock pulses, how many we are sending, multiply with that many count will give us the time period of this. So number of counts, as it is 16-bit timer, the maximum count is FF. The count which we are loaded into the TL register, TL0 register and TH0 register is FF, F2H. As the count is starting from 0, we are going to add +1. So now we will subtract FF with FF F2, which it is going to give as F is 15, 15 minus 2, 13, 13 is D, F minus F 0, 0, 0. So the count is D for this portion. For this we have to add 1, which is equivalent to 0, 0, 0 EH, which is 14 decimal. So once we calculated the count, then the number of counts multiply with the periodicity or time period of the clock pulse will give the delay, which will give 14 into 1.085 microseconds, which will give 15.19 microseconds. So this is the duration for half of the square wave. So the duration which we got is 15.19 microseconds, and for logic 0 also it will be wait for the same amount of time. So the total time period of the square wave is given as 2 into 15.19 microseconds, which will give us 30.38 microseconds. This is, let us assume if the count which it is loaded into the TL1 register is 7634, then what could be the time period? How we can calculate is, the maximum count is FF minus the count, that is 7634 plus 1. So we have to subtract FF with 7634, F minus 4, 15 minus 4, which is equivalent to 11, which is B. Next, F minus 3, 15 minus 3, which is equivalent to 12. F minus 6, 15 minus 6, which will give us as 9. F minus 7, 15 minus 7, which will give us as 8. Right? So for this we have to add plus 1 because the count is starting from 0. Now the total count is 89CCH. If we convert this one into decimal, which is equivalent to 35,276. This is counts. That means this many number of clock pulses which we are sending. Multiply this count with the time period of each clock pulse, that is 1.085 microseconds, which it is going to give 38.274 milliseconds. So the square wave it is generated with logic 1 for 38.274 milliseconds and the logic 0 for 38.274 milliseconds. So the total time period it is given as T is equivalent to 2 times of it, 2 into 38.274 milliseconds, which is gives as 76.548 milliseconds. Next, the third problem. Assume that XTAL will generate a frequency of 11.0592 MHz. What value do we need to load to the timer's registers if we want to have a delay of 5 milliseconds? And show the program for timer 0 to create a pulse width of 5 milliseconds on port 2.3. So on port 2.3, we are going to generate a pulse with the time period of 5 milliseconds. Right? And this is provided with XTAL1 and XTAL2 with a crystal oscillator for generating a frequency of 11.0592 MHz. So given the oscillator frequency is equivalent to 11.0592, the oscillator frequency divided by 12 will give us the periodicity of the clock pulse. So F clock is equivalent to F oscillator divided by 12, which is gives 11.0592 megahertz divided by 12, which will give us 921.6 kilohertz. The clock period for the clock pulse, this T clock is equivalent to 1 by F clock, which is equivalent to 1 by 921.6 kilohertz, which will give us 1.085 microseconds. The time required for delay is 5 milliseconds. So now we want to find how many counts are required. So the number of clock pulses are required are 5 milliseconds divided by 1.0485 microseconds, which will give 4,608 clock pulses. These many clock pulses are required for generation of a square. The maximum count in the register for 16-bit is, in the decimal, it is 65,536. The count to be loaded into the TL registers or TH registers are 65,536 minus the count number of clock pulses are required is 4608. So which will give 60,928 in the decimal. In the hexadecimal, it is equivalent to EE00H. So this count EE00 will be loaded into T0 register. That is TL0 will be loaded with the 00H. TH0 will be loaded with EH. And the pulse width which we are going to be measure are seen on P2.3. First clear 2.3. Now we are using the timer 0. So the upper 4 bits are 0. Whereas for the lower bits, that is for timer 0, we want to configure in 16-bit mode. So we write this one as 01. As a functionating as timer, we will write this bit is equivalent to 0. Gate bit is not required. So the value which we are writing is 01H into T mode register. Move T mode hash 01H. The count which we want to load into the T0 register is EE0H by moving TL0 as 00, TH0 as EH, as it is starting with a alphabet prefix with 0. Next, we want to start the timer. For that purpose, we will write setB TR0 for making the square wave at logic 1. We will make P2.3 as 1. Next, setB TR0. This is to start the timer 0. Check for overflow. If overflow is not occurred, stay in the same instruction. Once it is done, we can come outside. Here we are clearing P2.3. Clear TR0 to stop the timer. Clear TF0, that is for overflow. Then S jump to the L2 instruction. S jump or A jump. Anything you can use. As it is, distance is very less, so we can go for writing S jump. So these are the few programs related to timers, to functionate as timers, to generate a square wave on any port bit. Right. We have done a few analysis by taking program what it is going to generate. Then we have seen one more program for a generation of one more square wave with a given time period. Okay. Thank you all. I'll conclude this one. In the next one more video, I'll take the timers as counters also. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.